my screen now. So this is the part of Iceland that was part of the presentation, and it's high resolution sampling of volcanic eruptions. And it started off at Fagradalsfjall here. And let's quickly see that this gets to work. And yeah, so a quick word about Iceland. It's of course sitting on a spreading ridge. But it's not only that, because the spreading ridge in the Atlantic is extremely long and only very small segments of it are above the ocean. So there's something else going on in Iceland, and that is, of course, the Iceland plume, the plume that sits on Iceland. This is a hot spot that comes from deep inside the earth, bringing up material, and this causes Iceland to be actually above the water level. And the transform fault, the plate boundary, is a complicated one. It's actually shifting, it's shearing against each other. People call this a leaky transform fault. And this is what we're seeing here in the south of Iceland, in the Reykjanes area. So it's not just two plates drifting apart, it's actually more complicated here. And there we have various volcanic systems, 5 volcanic systems, in fact, and Svartsengi is one of them, as is Fagradalsfjall. And the area here had multiple eruptive episodes where there has been a whole series of eruptions. And over the last few thousand years, we had 3 major eruption periods, each of them separated by a gap of some 800-900 years. And now we have the one here at Fagradalsfjall starting. And well, worse yet, Svartsengi has just started as well. So here we might be seeing the start of a big new eruption cycle. This is why scientists believe that this could now spread to the entire peninsula over the next years and decades, and potentially could mean that a lot of eruptions might be happening in that area for some time to come. Now, let me quickly summarize the previous activity. In March 21, the Geldingadalir eruption started, and there was a long fissure system, 600 to 700 meters, that opened, and eventually by April, it developed into multiple craters here, and the lava outpouring was reduced and the individual craters developed. So there's a crater row that developed here, and by May, only one of these vents was really strong, vent 5 initially, and this gave rise to these spectacular sceneries and footage of the lava lake and lava pond overflowing. And this is a shot from early in the eruption. There you have vent 1 and vent 2 and 3 and etc. And vent 5 being in the center here. It's actually quite small at that point, but if you look towards the end of the eruption, vent 5 was actually the one that grew the strongest. Vent 5 was quite spectacular and was also longest going. And here you have a view from above from a drone, and there you have this beautiful lava lake with a crust on it. And of course, every now and then it was overflowing. And in June, for example, there was a rhythm going, that it was overflowing, calming down, settling a little, overflowing again, and was very rhythmic. And here I have a sequence of this. This is from a recent paper of ours. This is going back to June 8th, and there you see at 4:49 p.m. in the afternoon, in the top left, it's pretty calm, and then it's rising, the lake level is rising, and then it's overflowing, and then it's calming down, and this whole thing has taken 6 or 7 minutes, and then just 4 minutes past 5, just a few minutes later, literally, it starts again. And we try to explain this rhythmic, this pulsing behavior of overflowing there. And of course, it gave rise to these amazing images from drones from above. This is looking into the crater lake, and this is the rim of the crater lake. And this is one spot where it's piercing up, and the outflow would be, in this case, towards the right here. So, and eventually, the lava was also migrating south towards the Nátthagi Valley and the Meradalir Valley in the northeast. And in the image to the bottom right, we see the lava going to the south, and spectacular landscapes here, the lava flowing into the lower areas. And this is a wonderful little video sequence. I hope it works now. And let's see, yes, so here you see the Nathagi, the night pasture valley, because it's very sheltered. You see it filling up with lava over the course of just a few days. And then once it's filled, the lava is inflating, and therefore you see that the lava had movement inside, the lava field had movement inside, and was also being pushed up by gas that was coming out of solution, forming bubbles effectively. So, and let's continue here. Oops, no, I don't want that again. So here we've taken, of course, a lot of samples in the area. And here is a map of the Geldingadalir lava field and all the samples we've collected. But later on, we've also collected the Meradalir and the Litli-Hrútur lava fields. The Meradalir eruption now is the next one to come. And here it is. It started off as a fissure as well, and the fissure was running up the hill here. And this was August 2nd to 21st in 2022. And eventually, again, a main cone formed. And this is the initial fissure here viewed head on. And the cone is just in the top center of that image. And there you can see the birth of a little volcano along this fissure. Actually, I'll afford you a look into a baby volcano that never grew big. And here it is at the end of the fissure. You see the little spatter cone that formed. But as you see, there's a foot for scale. It never grew very big. So then this is the cone, August 13th. Two vents were still active at that point. Eventually, only the central one survived, and that became the main cone of the Meradalir eruption. Here, August 15th, only that one was going. And here's a few impressions as well of us sampling at the time. So then hopefully this works. There's a little overflow sequence here, flying over the eruption. And here on the right hand, you see the lava field, the Meradalir lava field. The lava was mainly flowing over the 21 lava field, but here in the north, it was actually going a little bit onto fresh ground. So the lava field in its entirety was expanding. Oops. So here you see the expansion. This is an image on the northern end. And there you see the 22 lava on the ground that was not covered by 21 lava. And in fact, this place here is that place here. And again, this is also sampling at the time in a systematic manner, trying to get a high resolution time series. So here is the lavas of the Meradalir coming onto the 21 lavas of Geldingadalir. And once you realize the lava is coming, you go out there and sample the 21 lavas again, just in case you're missing something. And within an hour, it looks like this. You have the new lava arriving, covering up the lava you've just sampled. And it's convenient because you just wait for the new lava to arrive, and then you can sample that. So you actually get a 21 and a 22 sample in one trip. So this is us then sampling the 22 lava that has just come over the 21 lava. So the Litli-Hrútur eruption that happened then in 23 started July 17th until August 4th. And this is now the right lava area on the map here, the red one on the right. And there fissure opened up once more, and a cone, one major cone formed, and the cone is the picture here. And you see the ground around the cone was pretty pristine here. This is a view from the west. Initially, it was mainly draining to the south towards the Meradalir Valley, but eventually it broke out on the western side and covered the area to the west as well. But it continued flowing south, the main lava flow that is. So here you now see the western breach on the lava crater, and initially it was evacuating the lava here, but then that area here broke, forming this large lava pond that eventually, however, was still flowing to the south because this is what the topography allowed. So this is a little video clip from Will Moorland, who had a drone up there. So now you can look into the crater. I mean, these images to the right, they show you how the crater looks from below, and this is how it looks on the inside. really a boiling pot of lava, if you will. So now here's a few images from the Meradalir area. This is my friend Lucas standing there on 21 lava. 2021 lava and the 2023 lava coming on. So there we have a gap, a stratigraphic gap. The 2022 lava is missing. And this is important to note because in the geological record, we couldn't really work this out. But here we can actually see what's going on so that we have an incomplete stratigraphy, technically speaking. And let's just move on. So here's the 2023 lava flowing over the 2021 lava, a lava wall really coming on. You can see some incandescence there. And eventually the lavas were meeting up. So there is the 23 lava, there's the 22 lava resting both on the 21 lava. And here we have a close-up picture, the two lavas about to meet. And the progress is very slow at that point, but eventually they overlap. And in the area, in the map here, there's one area here where the three lavas are resting properly on top of each other in a stratigraphic order, the Geldingadalir, the Meradalir, and the Litli-Hrútur. And here's us standing at that place where all the three lavas are properly above each other. Well, I guess we are very proud to look at this place as if we had hunted a lion or so. And this is the only place in the eruption sequence at Fagradalsfjall where we have all the three lavas in the right order. So then a game changer at the Fagradalsfjall was actually the new protective suits. They are very nice. This is from the University of Buffalo, but there was also others that were sponsored by various steel manufacturing companies. And while sampling before got a lot of interest, the sampling on the lavas with these suits got even more interest, and suddenly it took off on YouTube with several million views, actually 46 million views for some of the sampling sequences. The comments weren't always nice, but certainly a lot of interest, I would say. So, and now a few words about the sampling itself. So there's different lava types we sampled, of course, from 21 to 22 to 23. And I don't want to go into details now, but here is some of the geochemistry from our paper, that is Bindemanedal 22, which we published in NatComs. And there we see a strong change in the first few weeks of the eruption up to about day 40 or day 50. And then it peters out, it plateaus out geochemically speaking. And here we have trace element ratios versus trace elements, or trace element ratios versus trace element ratios. And there we see that there's a variation. The August samples are covered in yellow color, and the darker ones are earlier in the eruption, and there was a change. We initially interpreted this as a change in mantle signal, as did other groups. And this is maybe something I'm revising a little right now. Maybe we were all a little too quick with this, but we certainly see a chemical change there. How does this chemical change come about? Initially, the idea was that there's tapping of distinct mantle sources, mixing of distinct mantle components, or mantle melting at various depths, i.e. that the shallowing of the melting zone might play a role here. And this was also proposed by Halderson et al. So a mantle process that would cause these changes. And there's various end members described for Iceland, and I'm listing them here: the Snæfellsjökull end member, the Eldgjá end member, or various depleted end members, which are labeled DIP or D1 and D2. And the samples from Fagradalsfjall, they span the area in between them. So an interesting component then that afforded us to look into the situation in more detail was the different mantle components would then allow us to test whether there was different oxygen isotope compositions. And we know in central Iceland we have low oxygen isotopes in many of the eruptive sequences, and there's a dispute if this is a crustal or a mantle feature. So if initially we had a mantle distribution or mantle changes, component changes, we can then check whether there is also a change in the oxygen. So here on the plot on the right, we see central Iceland and the whole around eruption of 2014 plots here, very low values. This is a usual mantle value here at 5.5. This would be about here. Atlantic Moor and Reykjanes Ridge usually falls here. And The Fagradalsfjall samples, they plot very close to that. So this is our sequence. There wasn't anything out of the ordinary. And here's our timeline. It's actually rather monotonous, which then led us to conclude that if it's different mantle components that have contributed, they are not particularly different in oxygen isotopes. And if correct, then the implication would be that the low delta 18O, the low oxygen isotope signal in the center of Iceland is maybe not a mantle-derived feature, but a crustal feature. So we got this published in June, end of June 22. But as I said, just weeks afterwards, the Meradalir eruption continued. The sequence and the paper, well, has to be updated now to a certain degree. This is unpublished data, the Meradalir data here. They are confirming the sequence. There's a bit of diversification, partly because magma is stored. It will interact with the country rock. It will also fractionate a little. But overall, the sequence holds. There's no anomalous values here. And this seems to be also the case for the later eruptions, the data of which we haven't plotted yet. So then another feature here that came out in this paper, Radu et al. 23, was that we did barometry and water contents from pyroxene, and the pressures we derived were actually crustal, not mantle. So we have to be potentially a little careful about how to interpret our sequence. So this is the model we proposed, and we had a crustal system here at greater depth above the mantle level, but a mush system with a liquid center and potentially some melt lenses high up in the crust. So whether this is entirely true, I don't know. Maybe this reservoir is a little too deep. We might need to change that a little. But other proposals were that it's coming directly from the mantle with no crustal storage. And I don't think that holds true at the moment, particularly since we have these new data, and that is osmium isotopes. And these osmium isotopes, they are particularly strong in the first few weeks of the eruption, and these have to be crustal. So the initial eruptives of the 2021 series certainly look to be crustal in nature. Now, so how does the Svartsengi eruptions fit in? In December last year, the Svartsengi started off, and I don't want to talk very much about it, but we have this upwelling or this land rise in the Svartsengi region around the Svartsengi power plant, and this is leading to several smaller eruptions. They are green here on the map, so they are a little offset to the west from the Fagradalsfjall eruptions. And well, protective dams have been very, very helpful in preventing the worst. But of course, inside the protective dams, there has been a little fissure opening earlier this year, and several of the residents' houses got destroyed. So is Svartsengi a new system, or does it connect? And well, here's a potassium over titanium versus MgO plot. And this is the initial lavas from the 21 eruption. This is the Meradalir. This is the Litli-Hrútur eruption. And the Svartsengi seems to continue. In a timeline, it looks like this. So we have this initial strange change that we're not entirely sure about, whether it's crustal or mantle components. I'm starting to think crustal is the better interpretation, but then afterwards we have a rather continuous sequence. So there's one outlier here. I don't know exactly why that's doing what it's doing, but it is what it is. So, and otherwise this is a continuous range. So I'm confident actually that we are seeing a similar magma type being erupted there rather than a completely new magma system that is forming there right now. So when we look at the rocks here, then this is an image from Lucas's paper that just came out. I made a report about this recently, and there we have plage and olivine in there, very little pyroxene, and here we sampled it, and this is the data we published from the Geldingadalir, Meradalir, and Litli-Hrútur eruption. And now we have new data, and this is the Svartsengi data. I'm going to show that here. We're just writing this up for publication at the moment. And here we see the red and orange values. and that is olivine crystals and olivine microcrystals in the Sundhnúkar eruption from December, and they seem to continue the trend here. So there's a trend from 21 to the later Fagradalsfjall eruptions, and that's the Sundhnúkar eruption. So there's a nice trend, and it's offset from the average Atlantic mantle, and it's going towards the OIB field. So that's a plume-related component then. And this is consistent with this plot here, manganese over zinc. And there we also see a trend that continues. And if these trace element ratios are something to go by, then the dominant mantle source here would be periditic with a lesser pyroxenite component, and not exclusively periditic, but dominantly so. So again, this would imply that the magma types are related, and this would allow us to make some speculations. On the left hand in the lower panel C, we have this idea of a pure mantle-fed scenario. In the middle, we have several smaller crustal reservoirs, and on the right, we have this idea of a large crustal reservoir that's extending under the entire peninsula. The one on the left is a risky situation because it could mean we could have fingers poking up pretty much anywhere at any random point. The situation E on the right means we could have actually multiple fingers coming up. The situation in the middle, D, is probably the most friendly situation in terms of surface events, and there we might have small eruptions popping up above the reservoir, a little bit offset maybe because there's some lateral flow. And the good news from the initial geochemical data that we have is right now it looks like option D here is the best one. If the eruptions continue, if magma supply does not wane, then we might actually over the next decades move towards option E, but that's not what we're seeing right now and today, but it cannot be excluded to be a phenomenon that might actually have to be envisaged in the future. So I think there's reason to stay positive, at least for now. Hopefully this will not come to option E, because then we might have multiple eruptions on different points along the peninsula. So in this way, I'm going to say thank you very much for your time, and I hope you found that useful. So I'll stop sharing now, and I say hopefully you find it interesting when I do these little reports and record some of these talks. And yeah, thanks a million. All the very best, and talk again very, very soon. Bye-bye.